So, hi everyone, we wait a few more minutes.
Exactly, it really is, but taking a long time to see it that way. I could feel it.
Yeah, the thing is that they really need to do it carefully because it's not just components, right?
That's right.
So, tolerance of the double condition, say,
my moments.
Okay, welcome back to the afternoon session. We have two more talks. We start with Daniel Munoz from Queens on third order cumulants of complex Wigner matrices.
Okay, so first of all, can you hear me? People in Zoom? Okay. Okay, so first of all, thanks to the organizer for making this possible. So as you can see, I'm going to talk about the third order cumulants of complex Wigner matrices. So this is basically like the idea of the first and second order, and then we push it to the third order. Okay, so let me get started by defining what a Wigner matrix is. So by a Wigner matrix, I'm going to mean like a self-adjoint matrix. So the Xij entry is like the Xji conjugate. And also I'm going to have like the independent entry entries like usually. So the independence is going to be like all the ones above the diagonal are going to be independent, but also the ones on the diagonal, and also among each other. And I need to put some restrictions on the moments of the entries. So basically my random variable is basically my matrix is like a matrix with random entries, and the random entries are random variables, and I need to put some assumptions on the moments of these random variables, okay? So first of all, I'm gonna ask for the expectation to be 0. And because I'm working with complex random variables, I'm gonna ask for the expectation of the square to be 0 as well. So this second condition on the expectation of the square is just for all, not j, because the elements on the on-diagonal elements are, of course, real random variables. Okay, and I'm gonna ask for the expectation of the absolute value to the square to be 1. So if you can see these two assumptions in here, those are like the usual assumptions one do on like in the central limit theorem, that we have like mean 0 and variance 1. Okay, but because we are interested in finding like the third order moments, then we are going to ask for some hypotheses or assumptions on the third cumulant. And basically, I'm going to ask for all the third cumulants to be 0. This is just to guarantee that the third order moment exists, because otherwise, as we are going to see, the third limit is defined, the third order moment is defined as a limit. And if I don't do this assumption, then the limit just doesn't exist. Okay, so I'm going to ask for the third cumulant to be 0. And also, I'm going to ask for all the moments of the Wigner matrix to be finite. In this one? No, this is state 3.
They are independent, so the cumulants are still otherwise.
Yes. Okay, so now I'm going to define you what the high order moments are. So fortunately, Jamie and Octavio and probably Elba was talking about this definition of high order moments, so you are already familiar with this. But anyway, the high order moments are defined. So I'm going to consider like my Wigner matrix, and I'm going to take like some integers m1 up to mr. to be I'm going to define the R moment alpha m1 up to mr to be defined like this limit. So I'm going to take the limit when n goes to infinity. That's the dimension when n goes to infinity. And I'm going to consider like the R cumulant. This is just the R classical cumulant. So far I haven't introduced anything about free probability. It's just classical probability so far. And I have the R cumulant, and on the inputs, I'm going to put just the traces of some powers of my binary matrix. So I'm going to take x to the m1 up to x to the mr. And by the way, just to make the notation just like shorter, this n to the r minus 2 times the R cumulant is just what I define by alpha n1 up to mr sub n. Okay. Yeah, that would be xn. Yeah, I'm sorry, that's a typo. I'm actually thinking that this is not probably the correct slide, the right slide. It's probably the old version. So probably there's a lot of typos. So it is okay if I just change the light because probably I'm gonna need some. So just give me 2 minutes. No, I have the file on my USB, so it's gonna take it 2 minutes because probably there are a lot of typos in this old slide. Yeah, I better change my file. Yeah. Yeah, I'll be back in 1 minute. Yeah, this is the right one. Yeah, look at the n is not in there. So now I got the right one. So there will be no typos, hopefully. Okay, so I define like the alpha n1 up to r moment to be that limit, and just like some motivation, let's gonna see what's happening when we take like r equals 1 and r equals 2. So when r equals 1, this is like the usual limit of the expectation. The first cumulant and the expectation are just the same, and we take that normalization of the expectation. And all of you are already familiar that when we take the limit when n goes to infinity of that expectation, that converges to something, right? At least in the binary symmetrical law. And when we take like r equals 2, then we have like the covariance of the traces, and that's in literature is called like the fluctuation moment. So it's quite interesting going to higher cases. And to motivate this even more, let me just talk you about what happens with this binary matrix when I consider like r equals 1. Okay. So when I have like r equals 1, then that limit of the normalized expectation is going to converge to the Catalan numbers when m is even, and it's going to converge to 0 otherwise, right? So that's the so-called binary symmetrical law. But we can also write that in terms of non-crossing pairings. So everyone knows that the non-crossing pairings can be counted by the Catalan numbers, right? So when basically I'm saying that the first order moments of m are given by all the non-crossing pairings on m points. So this is a quite short and nice result, but we can also rephrase the same result in terms of the cumulants, the free cumulants. Okay, and I'm gonna say, basically saying that the moments are the number of non-crossing pairings on m points is exactly the same. Is exactly the same that saying that the cumulants are all 0 except when m equals 2. Okay? So this kappa m is what we call the classic, the free cumulants, and the usual k, that's what we call the classical cumulants. So I'm using basically Jamie notation. And those two results are basically analogous because we have the so-called, the well-known moment cumulant relation. Okay. Right. And then let me just say something before I go to the next slide. What about the case R equals 2? Okay, basically the fluctuations of this covariance. Okay. Okay, there is something similar in the case of fluctuations. That's from 2020 from Meo, Mingo, Chen, and Speicher, that they can express like the fluctuation moments in terms of non-crossing pairings as well. So I think that the fluctuation moments were analyzed even before, but the importance of this result is that it's quite similar to the previous expression because we are expressing like the second order moments in terms of the non-crossing pairings. Okay, and we have that the fluctuation moments alpha n1 and 2 is given by the set of all non-crossing pairings, some n1 and 2 points, plus 4 times the number of non-crossing pairings. And this sub2 means that we have taken like exactly 2 tree strings. So we know that we have, let me just do an example. Where is the tool? It's over here. Okay. So when we have like R equals 1, we know that we can draw like the non-crossing partitions on a circle. And when we go to two circles, I mean, second order, then we are going to draw like 2 circles with the end points on clockwise direction on the other circle, and end points on the inner circle on anti-clockwise direction. So this will be n1 and 2 up to m plus m. And we are going to say that the partition, I mean, in this case, we are talking about permutations. We are going to say that the permutation is non-crossing when we can do like the drawing of that permutation. In here, we must put arrows because we have like some direction on some order on the cycles. And we are going to say that it's non-crossing if we can like make the drawing so that there is no crossing between the arrows. Okay, so that this sub2 in here means that, okay, these are probably not the best examples because I have cycles of size 3, but when I say NC2, that means that all the cycles are of size 2. So I can represent just by lines. I just forget about the arrows because there is only one cyclic order. And that sub2 means that I have like exactly 2 tree strings, and all the rest is just connections in within the circle. Sure. This one? Oh, okay. When you put the arrow, it's because you represent like the order of the cycle of the permutation. Yeah. So if you have something like, let me do it in one circle, but in one circle the order doesn't matter. But if you have something like 1, 2, 3, this will be like 3, 2, 1. So that would be like the cycle of the permutation. Okay. And this K4 in here, that's just the classical 4 cumulants. So this is just the classical cumulants. And those are going to be the classical cumulants of the off-diagonal elements. So I take like 2x1, 2, and 2x2, 1s. Okay, and I have this. So it would be interesting to, right, now that we have like an expression for the second order moments, it would be interesting like to rephrase the same result in terms of free cumulants, just like we did in the case of one circle, right? But in order to do that, we need to give sense to what are the second order free cumulants. So in order to do that, I need to introduce the set of partitioned permutations. And so I'm going to introduce that very briefly because it's not like the main topic of the talk. Unfortunately, Jamie is here, so probably he can talk us if there is some question about that. But we have, and let me just like give you like the most brief definition of what are the partitioned permutations. So by a partition permutation, I'm going to mean a pair B pi, where pi is going to be like a permutation and B is going to be like a partition. Okay, and we're going to have this order pi less or equal than B, and that means that every block of B is contained in a block of every block of pi is contained in a block of B, and we are going to denote the set of those partition permutations by TSN. Okay. And then we can assign like a length to those partition permutations. So the length of the element B pi is going to be just 2 times the length of B minus the length of pi, where the length of those elements B pi It's just the usual length in one dimension, just the number of points, and you subtract the number of cycles. And the same with pi. And with this length, you satisfy the triangle inequality. The length of B sub u is like the smallest partition. I mean, partition such that it's greater or equal than B sub u is greater or equal than B and is greater or equal than u. Okay. And in here, in P sub sigma, this is just the composition, the initial compositions of permutations. And we have that the length of this guy is less or equal than the sum of the lengths of the other two guys. Okay. And then we are going to define the product last as B pi times W sigma to be precisely B sub W comma pi sub sigma if the inequality on the triangle inequality becomes equality and zero otherwise. This is something Elba was mentioning on his talk, on her talk. Okay. Okay, and now this is just like the set of all partitioned permutations. So it would be nice to have like something similar in the set of non-crossing of planarity, and that's basically like the set of. This is like the first one is just like a set of partitioned permutations. So now I'm going to define like the set of non-crossing partitioned permutations, and the set of non-crossing partitioned permutation is going to be defined with respect to any partition permutation u comma sigma. So I'm going to fix like u comma sigma partition permutation, and I'm going to say that another partition permutation b pi is going to be non-crossing with respect to the fixed element u comma gamma. If we have like this product is precisely the right hand side of the equality, and we are going to call to all those guys satisfying this equation to be the set of u comma gamma non-crossing partition permutation. This is quite similar to what happens in one. Let me just remind you what happens on the first case, because it's much more intuitive when we do that. So when we have a circle, just one dimension, we usually put like the elements 1, 2, 3, 4, 5, 6, 7, 8, 9. And we use you would put like the elements 1 up to some number, let's say just 9 in this example, in clockwise direction. And then we say that for a partition, if we can think of the partition also as a permutation, partition, let me just do one example, one random example like this. So I'm going to say that pi equals 1i, 2a, 3, 5, 4, 6, 7. This is going to be non-crossing because we have like the non-crossing condition on the diagram, right? Because we can also say that pi is gamma 9 non-crossing, where this gamma 9 is just the permutation, which is like basically labeling the elements on the circle. So that would be like 1, 2 up to 9. Right? So if we switch the order of the elements on the circle, well, then we make sense of what is a non-crossing permutation with respect to that another permutation gamma. So we usually forget that gamma because it's like understood on the behind, but basically we can define like a partition pi to be non-crossing with respect to a fixed permutation. Okay, so this idea is trying to capturing the same idea, but in the case of second order. So we are fixing like a partition permutation u gamma, and we are going to say that it's non-crossing with respect to that partition permutation if we have this equality in here. And why is this? Yeah, it would be nice to. Would you say a formula? You mean like an algebraic expression? Yeah, you mean the one in terms of the moment cumular relation in second order? You mean like that?
I put up the first 4 or 5 moments.
For the first order, we have this.
Yeah, okay, there is one too. Maybe it's on the next one.
Yeah, probably it's on the next slide. Is the moment cumular relation. Yeah. Okay. So why is this like capturing the idea of the first order case? Okay, if we take the special case where gamma is just gamma m, that would be like all the elements 1 up to m all in a single cycle. And we take like u to be the partition 1M, which is the partition where every element is in a single block. Then the set of non-crossing partition and permutation with respect to that fixed element looks like all the pairs 0 pi comma pi, where pi is non-crossing. This 0 pi means just identify pi as a partition. So the cycle of pi just becomes the blocks of the partition. And this is basically isomorphic to the non-crossing partition. So this is capturing like the idea of the first order case if we fix like these two elements. So this is giving us an idea of what consider when we go to higher orders. Because when we usually go to higher order, let's say second order, instead of consider one circle, we are going to consider two circles. So instead of consider gamma to be a permutation with a single cycle, we consider a permutation with two cycles, right? And that's the next slide. So we are going to denote by PSNC M1 M2, but that's basically the set of non-crossing partition and permutation with respect to this fixed element 1 N1 plus N2 comma gamma N1 comma N2, where gamma N1 comma N2 means just okay, this would be like first order. And then I'm gonna do here second order. And in here we were considering like gamma 9. So in here we consider like gamma N1 comma N2, which is now consisting on two cycles, 1 to up to M1, and M1 plus 1 up to M1 plus N2. And by the way, when I say M, I just mean the sum of the MIs, just for sure. And when I consider this, the analogous to those non-crossing elements will be like non-crossing elements on the circle. And in here we are going to see that. Let me just do two small diagrams. Okay, so in the case of one circle, we realize that the set of non-crossing partition permutation with respect to that fixed guy recovers the set of non-crossing elements. When we go to second order, we're going to see that there are basically two cases. And I described the two cases in here. So I probably don't need to do these examples. I have one example in the next slide. Okay, so when I go to the second order, the first guys are going to be like 0 pi comma pi, where pi is a non-crossing permutation on two circles. So the representation will be something like this. Union, these another guys, B pi, where pi is going to be like non-crossing on each circle. That means that pi basically, there is no like, we call it like a true cycle, but there is no true cycle because all the cycles are contained in the same circle. So there is not like one cycle going from one to the other circle. But then the role of B is precisely making the union. So B sub gamma has to be 1, and the length of B is the length of pi plus 1. That means that every single block of B is a cycle of pi set by 1, which is basically joining two cycles of pi, one from each circle. Okay, and actually I did two examples in the next slide, but before I go to that slide, just let me remind you that this first set is what Jamie called, well, this is basically isomorphic to the non-crossing permutations on two circles, but this second guy, this second set is what Jamie called PSNC M1 and 2 prime. That's probably the best notation we have found so far. So I'm just gonna keep with that notation, PSMC M1 and 2 prime. And if I consider like the union of these two guys, then I recover the set of partition and permutations in two circles, which I just denote by PSNC M1 and 2 just for shorter. Okay. So basically, I'm generalizing this idea to second order. Well, James generalized this idea in his paper. And then here I did two examples, which are basically like those. Okay, I didn't complete the other example, but in here there's one. So on the left-hand side is just a non-crossing permutation on two circles. So in here the arrows means that the order goes like, let's take like, where is the, okay, here's the permutation. 1, 2, 3, 9, 10. If you go to the arrows, you are traveling like around the arrows, and you go 1 to 2, then to 3, then to 9, then to 10, and just go back to 1. So that represents that cycle of the permutation, right? And in this case, those cycles are joined by some cycle, which we call just a true cycle. And the second, on the right-hand side, I have like the other possible case, where is that all the cycles of pi doesn't join the circle. So if you look at In solid lines, those are like the cycles of pi. In this case, everything is of size 2, so I only have cycles of size 2. So the cycles of pi would be like 1, 4, 2, 3, 5, 6, 7, 8, and 9, 10. Okay, and then when I do like the dot lines, I mean that I'm making the union of these two cycles of pi to make a single block of U, and that would correspond to the block 1, 4, 5, 6 of U. So these two pairs, on the right hand side, the permutation, the partition, on the left hand side, the permutation, that would be like a partition permutation, and PSNC. In this case, I have 1, 2, 3, 4, 5, 6, 6, 4 prime. Okay, and then I can. This is probably what was your question, Masood. And we can define like the second order moments in terms of the second order cumulants. So in first order case, we have like the usual definition of the first order moments in terms of the first order cumulants, and we can translate that to the second order case when instead of considering like the non-crossing permutations, we consider like the set of all non-crossing partition permutations on two circles. Okay, and in here I consider like kappa u comma b, where kappa u comma b is given by this. So I basically just run over all the blocks of u, and because we know that u is less or equal than pi, then every cycle of pi is containing a block of u, and then I consider like the corresponding, if those b1 up to bo are in this block of u, then I consider just kappa of the the size of b1 up to the size of bo. So that's quite more clear probably if I take this example in the previous slide. This would correspond to every block in solid lines will correspond to a first order case. So that's like kappa 2, kappa 2, kappa 2, kappa 2, kappa 2. I'm sorry, this one doesn't correspond to kappa 2, just the blue lines, the blue ones. But if you consider like the red ones, then that would be like a second order cumulant. That would be like kappa 2, comma 2. Those are like the two blocks, the two cycles which are being like joined to get like the block of U. Okay. So with this definition, we give sense to what are the second order cumulants. And then I can translate the same result I just showed before about the moments in terms of cumulants. So I just say that before that the second order moments alpha n 1 and 2 are given by this expression where NC2 is just the set of non-crossing theorems, right? But in terms of cumulants, that rephrase a lot easier, right? In terms of cumulants, you just say that all the first order cumulants are 0 except by the second one, and all the second order cumulants are 0 as well, except by the kappa 2, comma 2, in which case is 2 times kappa 4. K4, you're right, the classical equivalent, yeah. So probably, is that fine if I use that another bar? Okay. So just to have that result most clear. So if we consider like we have like the elements where we have like the two cases. So this is like case 1 that will correspond to the case of non-crossing permutations, and we have like the case 2 that will correspond like to PSNC MN prime. And in here everything is joined, but because we are considering only kappa 2 to be not 0, then we only consider like pairings. So otherwise we are going to have like kappa something different from 0, and that's just going to vanish. So we consider just pairings. And how many pairings there are? Well, the cardinality of the number of pairings, right? So M1 and 2. Okay, so that will come for the first guy, for the guys on the case 1. What about the guys on the case 2? Well, we are assuming that only kappa 2, comma 2 is not 0. So that means only a block like this will be valid, and on the circle just block size 2 because we still have the assumption that kappa 2 is not 0. All the other ones are 0. Right? So in here, how many guys there are? Well, basically, okay, that would be like the set of partition permutations P, S, and C. And let me just put that little 2, which means everything is a pairing. M1, M2. Okay, so that would be like the cardinality of this set, the contribution of the kappa 2, comma 2. But we can do like, let me just get some color chalk. We can do something like this. there is only one union of the cycles. So we can forget about those cycles and consider these two true strings. So we have this case, and let me use another color for the other case. And we have like, okay, just because it's over the same diagram. So probably I'm gonna draw another diagram. It's still in the camera? Yeah. Okay. Okay. And we have this another case like where we use the union like the other way around, right? So every element in here produces two elements in the set of non-crossing permutations with all the blocks of size 2 and with exactly two true strings. That's why we have these two factoring here when we consider just the non-crossing pairings with two true strings. Because it's basically like recovering all the partition permutations where everything is of size 2, I mean every cycle. Okay, so I'm rephrasing basically the same result of the moments in terms of the cumulants. And that is telling us that in some way the cumulants are easier to describe, easier than the moments. So we are gonna basically what I did with Jamie Mingo is that we pushed this to the 2 order case, and we got like an expression for the 2 order moments, but for the 2 order cumulants as well. That would be like the main. Okay, before I do give the main result, I need to define the 2 order cumulants, but that's basically like the same generalization of the 2nd order case. So now I'm going to consider all the partitioned permutations on 3 circles. And when I say on 3 circles, I basically mean considering this guy. Let me do that in large. PSNC and 1, M1 plus M2 plus M3. And in here, I'm going to take gamma, M1, comma, M2, comma, M3, where this is like the permutation with 3 cycles. And this is just the one partition, the partition 1, which everything is in a single block. So this is like the intuitive idea of going from 2nd order to 3rd order, right? So instead of considering gamma M1 and 2, I consider gamma M1, 2, and 3. Okay, and that said, PSNC 1, comma, gamma M1 and 2 and 3 is what I mean by PSNC M1 and 2 and 3. It's just for shorter notation. Okay. And this is an example of all the possible cases we get when we go to three circles. So in 2 circles, we got 2 cases, just either the circles are joined, or the circles are not joined, I mean by pi. But then you choose a single cycle from each circle, and then you do your union, and that's the big block of U, right? Well, something similar happens in the case of 3 circles. Now in 3 circles, either all the circles are joined, that would be like the easier case, and that will recover like the set of non-crossing permutations, and here it should be M1 and 2 and 3, that's a typo. So there was a typo, unfortunately. Okay, so that would be like SNC M1 and 2 and 3. Then I have the case where no circle is connected, and then I choose a single block from each one, and I join them all together into a single block, and that would be like a block of U, and that's what I denote by PSNC 111. 111 just comes from the fact that I'm choosing like 1 block from each circle. That's the easiest notation I found. Probably there's another one better, but that's the easiest one I just found. And then I have this other case where no circles are joined again, but then I choose like 2 cycles on 1 circle and 1 cycles on the other one, and I do the union like by pairs, like this way. And that's what I define by I denote by PSNC 211 M1 and 2 and 3. Again, 211 just the motivation coming from I choose 2 blocks in 1 circle and 1 block in another of the other 2 circles. And finally, I have the case where 2 circles are connected, already connected by a cycle of pi. So by the way, I think this is quite clear, but just let me mention that the black lines means the cycle of pi. And when I do like the red lines, that means those are the cycles of pi which I'm choosing to get to connect, and I mean to join to get a single block of U. And in this last case, I have like two circles which are already connected. Those are like the other big circle, and the smaller one to the right are connected by this cycle. And then the last one is not connected, but then I choose one cycle from this circle, one cycle from these another two guys, and then I do the union, and that would be PSNC, what I don't know by PSNC 1, in the sense that I'm choosing one cycle from each case. So those are the 4 cases which describe all the possible partition and permutations on 3 circles. I mean, non-crossing partition and permutations. And then I think I can give like the main theorem, and that's that I have an expression for the third order moments of n1, n2, and 3, and that can be expressed in terms of all the non-crossing pairings and the set of partition and permutations with some coefficients in front. So as you can see, this is a quite long expression, but it gets a lot easier when you consider the free cumulants. In the sense of free cumulants is just equivalent to say, okay, just consider 4 times K6 for the kappa 2, 2, 2 guy, and K4 bubble minus 2K4 if 2 of them are 1 and the other one is 2. And this K4 means the 4 classical cumulant, but of the on-diagonal element. I mean where the 2 indices are equal. Okay, so basically this is like the equivalent result in the case of 1 and 2, but now in the third order case, and it's still having this condition that the cumulants are a lot easier than the moments. Okay, so what time is it? Okay, so how much time do we have left? 25. Okay, that's great. I'm perfect. Yeah. Okay, so I have this theorem. So for the rest of the talk, just let me give you like a brief summary of how do we get to this result. Okay, so sure. Yeah, I think we don't have any assumption on the moment. So yeah, that can be possible. I mean, if you find a random variable satisfying those conditions, that's fine. And then get a distribution. Yeah, that would be like more a classical probability problem. Like, is there a random variable with K6 cumulant not 0 and 4 cumulant not 0? Well, I don't know. Yeah. Okay, so let me. Yeah, sure. Oh yeah, you are right. This is another typo, the second one in the talk. Yeah, you're right. So that would be like 1, 2, 1, 2, 1, 2, 2, 1, 2, 1, 2, 1. Otherwise, it doesn't make sense to consider the 6 cumuli. Yeah. Yeah, those are 4. Yeah, I just forgot 2. Okay. So that the sketch of the proof is just 3 steps. Step number 1. For step number 1, I'm going to consider some special graph, which we call basic cycles, and the motivation comes from traffic theory from Camille May. And basically, I'm going to consider like, okay, just let me fix gamma to be the permutation gamma n1 and 2 and 3, and I have like those cycles, and I'm going to consider like MJ guns. So the first one, in here, let me use with this example, is a lot much clearer. So in here I have like the graph Tn1, Tn2, Tn3 with the case M14, M26, M3A. So basically, I consider like 4 points on the first cycle, 6 points on the second one, at 8 points on the last one, and the arrow is always going anti-clockwise, so that 2 joins to 1, then goes back to 4, 4 goes to 3, and 3 go back to 1. So you close the cycle, and the same with the other ones. So this is what I denote by Tm1, Tm2, and Tn3, and the 3 of them together is just what I denote by Ta sub n1 and 2 and 3. Okay, and by the way, EI means the edge going from gamma I to I. So for example, in here, I have the labels in here. E1 is just this going from 2 to 1. Okay, so that's just a name for the edges. And probably there is something else I need to say about this, and that's like for a fixed edge, let's say E1, the vertex 1 will be like the target, and the vertex 2 will be like the source. So that's what I mean by source and target of the edge. I just say that because probably it will be in the notation on the next slide. Okay, so the step number 2, as you can see, it's pretty short steps. Step number 2 is rewriting this element alpha n1 and 2 and 3 sub n. That's the one where you consider only like the normalization of the cumulant without taking like the limit. So when you have like that guy, alpha n1 and 2 and 3, you write it like a sum over partitions, and then you sum over all the functions going from the vertices to n, such that the kernel of I equals pi, and then you have the third order. You have the third cumulant. This is just the classical cumulant, where the Ri's are just the product of x, and you run over all the edges. So because you are considering this kind of graph, and you run over all the edges, because those are cycles, basically you are capturing the idea of getting the trace. That's basically the idea. And then I sum over all possibles I, and then I just group them for the ones which are kernel of I equals pi, and then just move that to the front pi, and I sum over all partitions, all pi in partitions. So that's basically the idea. And that would be like an expression, like a shortened expressions in terms of partitions of that guy I'm interested in taking the limit of. Okay, step 3, the key fact. So I have this expression for that guy, for the one I want to take the limit. And for each fixed partition I can prove that the element inside the sum, that another sum, has order m to the number of blocks of pi minus m over 2 plus 1. Okay. So that's the key fact number 1. And the key fact number 2 is that provide that guy is not 0, I mean the one in the sum, then the order is bound by 0, which is amazing because it's proving that the limit exists. Okay. So basically, I'm reduced to counting all the partitions for which C pi is not 0. That means all this big sum, and this order is 0, because we know that these elements, this C pi has order number of n to the number of block of pi minus m divided by 2 plus 1. So I'm interested in all the partitions satisfying both conditions at the same time, and that's what we call a limit partition, just surviving the limit. And the corresponding quotient graph, T m1 and 2 and 3 and pi, is called the limit graph. So maybe you are wondering what's the meaning of a quotient graph. So I just did an example in the next slide. So
Can I ask something? So this is where you use that K3 0 to
yes. Yeah, but in here I'm taking like K3 of products of the random variable. So
I know that this is not 0.
yeah, that doesn't have to be 0 necessarily.
In the next step, we're using that.
Oh no, I'm using that C pi, which is all this giant guy is not 0. I mean, considering also the sum. Yeah, exactly.
Whether you need to switch, there was one case with the diagonal things that just blows up.
Yeah, that's the trace of the trace of the trace just vanishes. I mean, goes to infinity.
And it also does a lot of other terms as well, which makes the calculation easier.
Yeah.
But it's not a technical assumption. Actually happens is this one thing will grow order n, one thing will order 0.
Yes.
So you could change the regime, just play it in order 1.
Yeah.
That would be some other sense.
Yeah.
I don't know if it would be 3 problems. It would be, I don't know.
Okay, so I guess let me probably tell you what is the idea of computing this expression is that we have that alpha m1, m2, m3, n, and I write it like a sum over all partitions. And then in here I have another giant guy, which is the sum over all function going from the vertices to n, such that I have the condition, the restriction that kernel of that guy I equals. By the way, I didn't mention what the kernel, but I think that we are already familiar. Jamie was talking about that. And the kernel of I is just a partition of the elements where U and B are in the same block if U, E, and U, B are the same. So I have I U and I B, yeah. And I have this guy, and I have N to that order minus M2 plus 1, and then K3. And I have R1, R2, R3. This second giant guy is what I call CPi. So basically, just I'm assuming like all CPis, pi and all them a partition. And I want to look at, and I know that the order of this guy is N to the number of blocks of pi minus N divided by 2 plus 1. So I want to look for the ones, the partitions satisfying that the guy is not 0, but at the same time the order is 0. So those are the ones in the limit. When I take the limit, those are the ones surviving, right? Because I want to take like the limit of this element. That would be like the third order moment. So when I take the limit, I mean when I make this N goes to infinity, just survives the partition. I'm going to say in here survives the partitions pi such that C pi is not 0, and that order number of block of pi minus M divided by 2 plus 1 is 0 as well. So those are the one in the limit. So I'm interested in counting those partitions. And by the way, it is curious, but also when I identify what are the partitions precisely surviving in the limit, I can compute pretty easy the contribution C pi. That just comes from the structure of the graph, of the quotient graph. So I was mentioning the quotient graph, T pi M1 and 2 and 3. And by the quotient graph, I mean, before I consider like the union of the two basic cycles, right? So now I'm taking like a partition of M, which is just like a partition of the vertices of those cycles. So whenever I have like two elements in the same block of B, I'm going to identify the corresponding vertices. And when I get is something which we call a quotient graph. So basically the quotient graph is encoding exactly the information of C pi. And so basically we're interested in finding those pi satisfying those conditions, but that's the same as being interested in the partition pi such that, I mean, that can be described completely in terms of the quotient graph. So let me tell you what are the quotient graph which survives on the limit, or how those they look like. And we have four cases. In this first slide, I have two cases. On the left-hand side, that's what we call 2443 type. So that means that the quotient graph looks like the edges in black. That means that the ones coming from the first basic cycles, the edge in blue, that one's the mean coming from the second basic cycle, and the ones in red coming from the last basic cycle. So the quotient graph looks like this way. So I call it 2443 type. I'm basically motivated by Mayo, Mingo, Speicher, and Peche's paper, where they basically compute this problem in the second order case, and they get some pretty similar graph, and they call to some graph 2443 type. So that would be like the natural generalization to the third order case. So 2443 type is something which looks like this way, in the sense that I have two edges of multiplicity 4, and all the other ones are of multiplicity 2. And when I forget multiplicity, that means that I basically identify all the edges joining the same pair of vertices, then I get a tree. So whenever I have like two edges joining the same pair of vertices, I just consider that as a single edge. So that would be like a tree, right? It looks like a tree. And the same on the right-hand side. But now on the right-hand side, I just call it 263 type, because I have a guy of multiplicity 6, in the sense that there are 6 edges joining the same pair of vertices, and all the other ones are of size 2. Okay, so that would be like, this would be like the kind of quotient graph which survives on the limit, but basically the quotient graph is encoding exactly the same information of the partition. And then I have another two cases, which by the way, I separate these two cases because the contribution C pi is different from each one. Because if you look at the structure, that looks so similar, right? If I consider this cycle to be of size 1, then I get basically like this guy. So I just like shrink these two vertices to a single one, and I recover like that structure. So they look pretty similar. That can be actually described by the same idea. But the only reason why I describe these like in two different types is because the contribution is different for each guy. Why? Because in here I'm gonna have like, when I consider the trace, I'm gonna have like product of guys which looks like x11, x11. And in here I'm gonna have just like x1a, j for I different for j. So that's why I'm considering these two guys like in different cases. And on the left-hand side, this is what they call a 2-4 unicircuit type, in the sense that I have an edge of multiplicity 4. And if I forget the multiplicity of the edges, I have a graph with a single circuit. By a circuit, we mean what usually people call that a cycle. I mean, a graph which looks like this way, like a tree with a single, well, it's not a tree, but like a graph with a single cycle. And if you forget the cycle, then you get a tree or a union of trees. And on the right-hand side, I have the same structure, but now the cycle looks like a multiplicity 4, and this is like a loop, and this is what we call a 2-4 uniloop type. And finally, and this is the complicated guy, and this is the I did two examples, but both of them are considered like the same kind of graph. So this is what we call a double bi-circuit type. So double because all the edges are of multiplicity 2, and when I forget the multiplicity of the edges, I get a graph with 2 circuits, in the sense that I have like one circuit. Okay, let me just raise this. Maybe this. So in the sense that I have like 2 cycles, but by circuit we mean like what in literature is usually called cycle, but we just decide call it circuit because we are using cycle for the basic cycles. So this is much easier to read. So when we forget like the multiplicity of the edges, we get graph like this, like basically with 3 faces in the sense of Euler characteristics, and all the edges multiplicity 2, in the sense that when you double the edge, you get those ones. So we are interested in counting those. And now, okay, is it 10 minutes left? Is that right? Okay. Great. And now just let me just like a fast argument of how I counted those graphs. So this looks like it is easier to explain if I go to the case 1, because it's basically the same idea translated to the case of 3 circles. But when I have like one circle, actually when you consider one circle, and you consider like the same limit of that normalized trace, the quotient graph which survives on the limit looks like this way. Like this is what we call double trees, because it's a tree when you forget the multiplicity, and all the edges has multiplicity 2. And how do we count double trees? We can count double trees by non-crossing pairings. So this is like a graph. So if you those dot lines, if you join like any 2 edges by the dot lines, then you recover like the quotient graph. So you basically the double trees can be counted by the set of non-crossing pairings. That's why in the Wigner symmetrical lie, I mean in 1 dimension, when you take the limit, only survives the non-crossing pairings. When we go to 2 circles, something pretty similar happens. In 2 circles, there are 2 cases, I mean 2 types or 2 kinds of quotient graphs surviving in the limit. And let me just do a fast drawing of those. Okay, so we either have something like this. I'm gonna use, probably gonna use another color because the bar is green. So red, right, okay. Okay, so let me use color red for some of the edges coming from one basic cycle. Okay. Maybe purple. Let me try purple. Is that better? Let me do it like this way. Okay, so those are like the edges coming from the first basic cycle, and then on the second basic cycle, I have like edges, like in the same way. So this is what we will call, or no, this is what Jamie paper they call it like 2-4 tree type, and it's basically like a tree when you forget the multiplicity of the edges. All the edges has multiplicity 2, except by one which has like multiplicity 4. So that's why it's called 2-4 tree type. And we have that another kind of graph, of quotient graph, which they call 2, 4. In our notation, it would be double unicircuit type. They call it double unicycle type. But okay, let's just call it double unicircuit type. So double unicircuit type in the sense that you have like one single circuit, but you forget the multiplicity, and all the edges has multiplicity too. So you have kind of the same relation with the non-crossing pairings. As long as you take a non-crossing pairing, but with not two true strings, and you do like kind of the same idea of joining two edges, which are joined by the non-crossing pairing, then you recover a guy of double unicircuit type. But when you have two true strings, then you get like a 2, 4, 4, 3 type. So this is the idea of behind of counting the case tree. We still have that relation. When we take a non-crossing pairing, the quotient graph Tn1, oh, in here there are more typos, but in here it should be Tn1 and 2 and 3. And then you do the quotient under gamma n1 and 2 and 3 composed with sigma. That's going to be a limit graph. I mean, it survives on the limit. So you have the relation. And so that means that you have like a surjective function going from the non-crossing pairings to the graph you are counting. But of course, there are problems like that doesn't happen in the case of 1 and 2, but in the case on 3, it may happen that you have two different non-crossing pairings, and those are sent or those are mapped to the same limit graph. So that's like something which doesn't happen in the case of 1 and 2, but in the case of 3, it does. So that's a problem. But the good part is that almost all the valid graph, I mean, the ones I described before, these 3 slides, almost all of them can be counted in terms of the case 1 and 2. And I mean, in the case of first and second order. And let me use this example because this is like the more intuitive example, probably the easier one. And then consider like a 2, 6, 3 type. That means that a nation multiplicity 6, all the ones are multiplicity 2. And when I forget multiplicity of the edges, I recover a 3. Okay, if you look at the guy in white, I mean, just the one coming from the first basic cycle, that's a double tree. And double trees can be counted by non-crossing pairings. That's what we had in the first order case. The same with the one in blue, non-crossing pairings, but now in M2 points. And the same with the guy in red, but now non-crossing pairings with M3 points. Then once I select like once I like choose like the tree, then I need to make the union along some edge, which is the same. So the union can be chosen in M2 over 2 times M2, M1 over 2 times M2 over 2 times M3 over 2 ways. And for each way I do the union, I can do like 2 possible orientation for the edges. So I either do a union like, let me use this side of the board. Let me do that just with 2 double trees. So imagine that I want to make the union of these 2 graphs along these edges. So I can either do the union like this or the other way around, like this. You know, like flipping this and put it together to the other graph. Because each orientation contributes to a different partition of the vertices, which is the one we are counting. So that's why we consider like 2 cases. In the case of double trees, we have 4 different unions. And therefore, all these graphs, which is basically one of the possible cases, these ones, all these graphs can be explicitly counted by this expression, which is precisely, in here should be 4, which is precisely 4 times PSNC 1, 1, 1, M2, and 3, and 3, M1, M2, and 3. And this little 2 in here means pairings. So that's basically because I take a pairing on each circle, and then I choose a block from each one and make the union of the block to get a giant block of U. So this is 4 times the cardinality of this. That's the idea behind of getting to this element in here, 4 times the cardinality of that guy. And this case 6 should be like the contribution of the corresponding quotient graph. So that's basically like the sketch of the proof. If you want to see the proof in more detail, those are some reference. So this is the paper itself, and those are the ones we base most. And thank you very much, everyone. in words. Yeah, in words, I will say that. Okay, that's actually a hard question. It looks it looks easy, but it is not. I can say that only cumulants whose indices add up to something multiple of 2 survives. All the other ones are 0. I guess that multiples of 2.
Got that slide.
Yeah, only cumulants whose indices add up to a multiple of 2, that in this case is 2 plus 1 plus 1, that's 4, survive.
So the left-hand side is multiple moments.
On the upper, I mean this. Oh yeah, those are moments, yeah, which have like a quite complicated expression.
Right, so this looks like it means that also moment got the isomerization.
Okay.
They're also larger limit.
Okay.
I'm mistaken, I don't know.
Yeah, probably. I should need to give it a look, and probably there's a relation.
What is the right answer? So the right answer is
You mean that long expression? That's an explicit way of counting the moments in terms of partition permutations and non-crossing pairing. Yeah, but which is important is that equivalent. You can say that you can like basically rephrase the same result equivalently in terms of cumulants, which look a lot easier, right?
what would be possible application?
Well, we can think of it's probably the case where we have like the GOE, we have a lot of Gaussian entries. In that case, all these guys just become 0 and just the second first order survives. So usually, I mean, like computing directly from the, yeah, I think it would be easier. Yeah.
As far as I know, 8 minutes only. Don't have it. Is one thing. And those formulas are at all order and all generic.
Oh, you mean like the alpha n1 and 2 up to mr, and those are the pairings. Yeah.
And this is not.
Yeah. This.
Their formula doesn't.
Yeah, this is Wigner. You have like independence of the entries, and it's completely different. Yeah. You need another machinery for unitary.
In the case of,
Yeah, they explode. I mean, the theory doesn't require unitary. But the theorem. So actually, I don't know what the positive. I mean, that.
don't they use multiple recursion?
Yeah, for the genus greater than 0, yes, probably those ones and the lower order ones assuming unitary invariance.
They depend on unitary.
Right, so this wouldn't fit into their scheme, but even the formulas. So I don't think they have any ever looked at even. At least that's what I asked Elba. She never worked in. So there are a couple of when they haven't. Whether their formulas agree with others. Yeah. There's another thing that's connected to that is that from and those drawings, go back one screen, one of your pictures, not that one, front the graph.
The graph pictures.
Look at that. See, look at the left picture. Look at that. The one that has a 1,5, 15, right, just has a vertex with a 15. Very lower right hand.
Yeah, 15.
Pick that thing up, hold it inside the other part. Okay, and then take the blue thing up up, straight up, and fold it in. And then you've got a blue region, a red region, outside is a black region.
Oh, yeah, it's like a topological description.
A map on a sphere and all the pictures.
Yeah, with all the pictures, you can do that. So you can like describe the graph in 3 phases. Yeah, it would be, all these graphs are planar, yeah. Yes, and they split like in 3 phases. Yes.
Consider a case where you have circle inside circle or no?
Well, those usually just are like a way of drawing the non-crossings, but one usually consider like, you take like order R, you consider like R minus 1 circles inside and a bigger one.
Yeah, think about it as a bound, as a sphere.
Yes.
Okay, circles.
Yeah.
So you can't
Oh,
you can have one circle inside another circle. That's
yeah.
Because it's a sphere, you can't go down. I mean, that would be
The reason I'm asking is that similar
higher
diagrams,
genus, yes.
so I mean, similar diagrams appears in operands, to operands.
Okay.
And like moduli spaces of curve diagram, but they allow circles into circle.
Okay.
And having that, it allows defining some operations.
Okay.
But you can ask that same question for all of them. Right?
Yeah.
Because that's, I mean, he never drew it. For all of the pictures.
But he had all formulas, so it's like the other side of.
Yeah, I don't, whether, I mean, that's a big job.
I mean, this thing is also seems to me, it's like there are 2 texts. I mean, this is one text.
Yeah.
Other text really algebraic.
Yeah.
Has to be.
Sure.
Yeah, just your theorem. It's a little stage that you put the above formula as linearity of sets.
Yes.
Do you have a formula for that? Like, have a formula?
Yes, you can express that in terms of binomial coefficients, probably. Yeah. But do you think that looks more beautiful? I think this is nicer.
I mean, in my mind, the best version is that MNP is, and because the point is that the human.
Yeah, for sure, this is the one which is better. Yeah. Yeah.
So, and if you look at the early days of machine, people spent a lot of time explicitly parameterizing things and got giant formulas. Turns out the formulas have an NP every end. Right?
Yeah.
So when you use that thing, calculation, when you do all this complicated parameterization, it's Vandermonde identities, binomial coefficients, very complicated things. So this is another example of this.
Yeah, we gotta know it.
Okay.
That's okay, but we know that the machinery, if you present metric, that's just formula.
Okay.
Nobody needs to know what is ES.
Yeah, sure. Yeah. Actually, at the end on the last slide, I just showed that the cardinality of that set is precisely the expression, and those one are like a binomial coefficient.
The first statement of the theorem should be relegated to a and the main theorem should state that unless very rigid.
Okay.
That's the one question. For the higher order
Oh.
second order, I mean, object.
Okay.
He's saying, okay, the definition for second order will including the mentioned reason.
Okay.
So then I assume they should have analog central units.
About the high order freeness. I
And then convert it to the what they can show in the second slide. The kappa to
In the second order case, it's the same, all the,
Mhm.
and it's the same rule that all central limit groups that the scaling forces all the other cumulants to from the fact that having doubles is the fact that the arc for tendons. Look at all the ordinary by scaling with pro.
I think in Zoom, whether
Yeah.
okay, let's suppose.
Okay.
At 3:30.